The electrostatic potential inside a charged spherical cell is given by phi equals to A r square plus V, where r is the distance from the center. A, B, C are constant. The charge density inside the ball is. So here we have phi equals to ARP, that is your electrostatic potential, and we have to calculate the charge density inside the ball. So here the charge density inside the ball we have to calculate, and at a distance of r from it, if we look at, sorry, so at a distance of r from it, the potential is given by this equation, that is phi equals to a times r square plus b, and we have to find the charge density. So I will calculate the total amount of charge enclosed in this region, and then we will calculate the potential here. So total charge enclosed in this region will be written as q enclosed. Here if I write, then q enclosed will be 4 by 3 uh, here we have to understand another important point, that first of all we need to know this thing, that whether the density is uniform or non-uniform. We don't know about it. So what I will do, I will differentiate this function because potential is given. So if I write minus of d phi by dr, if I differentiate this function, I will get electric field, and if I differentiate it, then I'm getting here E equals to how much? E equals to minus of 2ar. So we got electric field, that is equals to minus of 2ar, and we know that electric field inside this solid sphere is rho r by 3 epsilon naught. Yes, so that is directly proportional to r, and here also you will find that here also it is directly proportional to r. So I can say that here charge density inside it is uniform. So considering that point in my mind, I will write E equals to rho r upon 3 epsilon naught, that will be equals to minus of 2ar, and here you will see r and r will cancel out, and you will get rho equals to minus of 6a epsilon naught. So this is how we can answer this question. We can also answer this question by another method also. I will assume here like that we have two, we have this is a sphere here, okay, and I will consider a small thickness. Let us keep it here also again. Okay, so now you just focus here. Here if I talk about the region, this one, if we talk about this region that I'm setting, so in this region I will say that the electric field, okay, this region here, here I'm saying that electric field at this point and this point, let's say this is E and this is E dash. So in this region we have electric field, and these electric fields are different. This is at r and this is at r plus dr, r plus dr. R plus dr, electric field at r and electric field at r plus dr. So if I write E at r plus dr minus of E of r, then I will be getting here, and area I will assume it to be constant also over there. So this is ER plus dr. If I write the flux in terms of a flux, I want to calculate it. So I'm assuming, although if you just write it like this way, better if I just assume this radius. So flux entering phi in will be how much? That is E at R into 4 pi R square. Similarly, phi out, that is the flux that is outward, that is E at R plus dr into 4 pi R is plus dr of whole square. This is what we are getting. So if I calculate total flux, phi total flux, then this will be phi out minus phi in, and this is nothing but this is E at R plus dr into 4 pi R square, R plus dr of whole square, basically R plus dr of whole square minus E R into 4 pi R square, this one. Now if we solve this one, this expression, it is little bit lengthier one, but we need to understand, because here we are going to discuss a very important point, that is phi total, and if I solve it, then I will be getting it as a E at R plus dr, and this is 4 pi R square plus 4 pi 8 pi R dr plus this is 4 pi times dr of whole square minus E at R into 4 pi R square. So if I take 4 pi R square common, this will be E at R plus dr minus ER, E at R plus dr, R plus dr minus of ER. And then other terms that we have, that is E R plus dr R plus dr into 8 pi R dr plus E R plus dr into 4 pi dr of whole square. You can see that these terms are very small, so we can assume it to be 0. So this is nothing but 4 pi R square, and this is dE, change in electric field. So this much amount of the flux, and that is equals to Q enclosed in that region by epsilon naught. Now if I write Q enclosed in this region, then Q enclosed, I will assume in that a small volume, I will assume rho to be almost constant, so I will be writing rho into 4 volume of that section 4 pi R square dr, rho into 4 pi R square dr, that's a volume, by Q enclosed, that is epsilon naught, that is equals to 4 pi R square, and this is dE. So here 4 pi R square and 4 pi R square will cancel out, and we got dE by dr, that is how much? That is rho by epsilon naught. So this is another important form of Gauss law in differential form, that is d by dr equals to rho by epsilon naught. Now look, the potential equation that have been given to us, phi equals to AR square plus B naught, phi equals to AR square, this is the potential equation, AR square plus B. So if I write electric field here, then electric field is minus of 2AR times 2AR, and if I write dE by dr, then dE by dr is how much here? dE by dr is nothing but minus of this is 2. So if I substitute the value, if I compare these equations together, then I will get here minus of 2a equals to rho by epsilon naught, and I can write rho equals to minus of 2 epsilon naught. So this is the most general way to solve this problem. Here we have smartly we have we know the equation that E is directly proportional to R for uniform charge distribution. So we got this one directly. Even we can also try this method also. That's a differential form of the Gauss theorem. And you can also solve this problem using that concept. V equals to potential inside the spherical cell is written as K, and this is Q by 2RQ, and this is 3R square minus of R square. Now I can compare these two equations together and to get the value of A and B, and so from there also we can get the value of Q, because I can further replace Q equals to as 4 by 3 pi R Q times rho, and then I can compare them and I can get the value of A and B separately.